Today I will be explaining question 10 on homework 2. The question reads, standing waves on a 1 meter long string that is fixed on both sides are seen at successive frequencies of 36 Hz and 48 Hz. What is the fundamental frequency and the wave speed? Draw the standing wave pattern when the string oscillates at 48 Hz. So before we start, let's outline what we know. We're dealing with a standing wave, meaning that each point on the wave has a constant amplitude. The places of minimum amplitude are called nodes, and the locations of maximum amplitude are called antinodes. The string is fixed on both ends like a guitar. Since it's fixed on both ends, one wavelength will have to be a whole or half integer, like 1, 1.5, 2, or 2.5. Coming back to the question, another thing we notice is that we're given a length. Length is equal to 1 meter. Let's keep track of that. Now back to the problem. We have two frequencies. Frequency A, we'll say, is 36 Hz, and frequency B is 48 Hz. For part A, we have to find the fundamental frequency and the wave speed. In order to get resonance, you have to hit specific separate values. This has to be exact. So imagine that these values are like a staircase. We can say that 36 Hz is here and 48 Hz is here. These are discrete exact spots. You could say it's like a ramp, but then that wouldn't work because we don't exactly know perfect distances. We are given these two successive numbers, 36 and 48. So we know that 36 Hz is one multiplier of the fundamental frequency, and 48 Hz is another. In order to find the fundamental frequency, a visual way of going about this is to look at the staircase and envision the difference between them. So we can say 48 Hz minus 36 Hz is equal to 12 Hz. That is the fundamental frequency. Does that make sense? It might help to work out the problem in a more official way to get that point down. Let's try looking at this another way. We can try to find the ratio for this problem by saying f of b over f of a, remembering that this is 48 Hz and 36 Hz respectively, which simplifies down to 4 over 3. This is the ratio that can be used to find the mode, which we'll call m, in this problem. Once again, we have to remember that these are given as successive frequencies, so we can assign the first one to m, and since one's right after the other, we can say the other one is m plus 1, and set this equal to the ratio that we just got, since they are equivalent. Then all you have to do is solve for m. So you can do m plus 1 equals 4m over 3. Solve that all the way through. We get m is equal to 3. Taking this value, we can put it into this formula. And we get this is equal to 36 Hz, which is the associated frequency with m, divided by m, which is 3, and we come back to 12 Hz again. So that's another way of solving part A. So this is option 1, and this is option 2. So we found the first part of question A, but now we need to get the wave speed. This is a lot faster to do, but you just have to remember that for wavelength, there's a different formula. You just input 2L over m, and so we get V equals 2L over m times the fundamental frequency. So we just input values from our information bank, and this gets us to 2L. And in this case for m, we're using m equals 1 because we're only interested in the first harmonic, just for simplicity's sake. And so we put 1 here, multiply by the fundamental frequency, which is 12 hertz. And that works out to be 24 meters per second. So our wave speed is equal to 24 meters per second. And that is part A. Part B is a lot shorter, and we're supposed to draw the standing wave pattern when the string oscillates at 48 hertz. Remember that vibrating strings vibrate at all harmonics of the fundamental frequency. So in our case, remember that this is equal to 12 hertz. So the number that we're looking for is going to be a multiple of 12 hertz. To find harmonics, there's a simple formula right here. And all you have to do is just input the values of m. So for F1, it's just going to be 1 times the fundamental frequency, so that's 12 hertz. That's equal to 12 hertz. For 2, just do the same thing, times 12 hertz. That is 24 hertz. 3, and 4. Now this is what we're looking for. So it turns out that 48 hertz is a product of the fourth harmonic. So the point of this is we're trying to get a wavelength, because in order to draw this out, we need to know what the wavelength is going to be within 1 meter. So we use this formula right here, keeping in mind that if it's the fourth harmonic, that means that m is equal to 4. So the wavelength of the fourth harmonic is equal to 2 times the length, once again that's 1 meter, divided by 4, because remember m is equal to 4, and we get 0.5 meters. So one wavelength is equal to half a meter. Keeping that in mind, this is how we're able to draw it. So that is 1 wavelength, 2 wavelengths, now there's a node here, 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 and here, and you're finding your antinodes in between. And that's it. I hope this helped.